And I am Alduheza from the Angelo and Diesel Electronics.
And I am Sebastian Carreon from Angelo and Diesel Electronics. And this is our video presentation on our CRC-12 and PWM PCB circuit. For the contents of this video presentation, we have the PWM and CRC circuit concepts, the PWM and CRC circuit and diagram, the LT spice or the simulation results, the PCB prototype results, and our learnings.
The cyclic redundancy check, or CRC for short, are the bits added to increase a digital signal's fidelity and integrity. Now, CRC offers a very reliable error detection and checking. Now, finding the CRC remainder is done by simply applying binary division between the input and the set polynomial. Now, before dividing the input, which is labeled g of x, it must be first appended with zeros depending on the number of, or depending on the degree of the polynomial. Now, the remainder achieved after dividing the message to the polynomial will now be the CRC code. Error detection for CRC is done by simply dividing the g of x, our input, with the remainder to the polynomial again. Now, if the output is purely zero, that means that our code is error-free. But in case that the output is non-zero, it means that there's an error in our message. Now, for this project, we'll be using CRC-12, meaning it will have a polynomial as presented here as x to the 12 plus x to the 11 plus x cubed plus x squared plus x plus 1. And simply the usual process of CRC will then be employed. Now, the number of zeros in this case will be 12. Now, in a circuitry, CRC-12 can be achieved by following the method or this logic. So essentially, we'll be applying the XOR logic whenever a term in the polynomial, which is labeled P of x, is present by the carry output, which will be labeled as the C12. And for the terms that are not present in the CRC-12 polynomial, there will be no XOR to be applied for these terms, and their output is simply just shifted.
For the concept of PWM, first we need to ask, what is PWM? Pulse width modulation, or PWM, is a powerful technique used in various electronic applications to control the average power delivered to a load. It works by encoding the desired power level into the width of a digital pulse string. Pulse width modulation can be used not only to control the average power delivered to a load, but also to represent an analog signal using a digital pulse train. This approach relies on varying the pulse width of the digital signal based on the amplitude of the analog signal being represented.
Hello, let me discuss our conceptual schematic first for our CRC-12 circuit. So let's start off with the switches, or push buttons. Switch 1 here will control the input, and switch 2 here will control the reset. So we only need 2 push buttons. And then here we have this LM7805 IC, which is a 5 volts regulator. Now this 5 volts regulator is crucial in our circuit since, based on their datasheets, majority of our IC has a maximum supply voltage of around 6 volts only. And using the 9 volt battery we have as our supply voltage will damage them. So it is essential to step down our supply voltage from 9 to around 5 volts to ensure that the ICs will work as intended. Then next, we have this 555 timer here, which will serve as our clock. Now do take note that the reset pin is connected to clock enable, which is crucial later. I will be discussing why. And we also have a little note here regarding the reset pin. If it is high, the clock must be enabled and the reset must be low if the 12 zeros, the appending of 12 zeros to the input has been done. So later, we'll discuss more about that. Next, we have a little note here to always place a 100 nanofarad decoupling capacitor for every single IC. Now, this decoupling capacitor will ensure that the supply voltage will be smooth for the ICs, and the IC will work as intended. Now, we have this 74164 IC. Now, this 74164 IC serves as our serial input, parallel output. So, as you can see here, we have C4, C5, C6, C7 up until C11 will be controlled by this 164 IC. Later, we'll discuss what those C outputs mean. And then, we also have this 74194 IC, which serves as a parallel input, parallel output mode of registering. So this 194 is used for applying XOR to the bits that needs to be XOR'd, basically. So we have here C1, C2, C3, since based on the block diagram presented earlier, they need to be applied with XOR logic. And then C12 as well. Alright. Now let's first check out the LEDs or our outputs. So we have C12 to represent the leftmost or the most significant bit, and C1 to represent the least significant bit. So all in all, we have 12 bits to represent our CRC12 remainder. Then we also have this green LED for our clock so we can time our inputs and our shifting of inputs synchronously. Next, we have these sets of XOR that will be applied to the polynomials or the bits that needs to be XOR'd. So let's take a look. So we have input to be XOR'd with C12, C1 to be XOR'd with C12, C2, C3, and C11 to be XOR'd with C12. And those XOR input C1, C2, C3, C11 will be the inputs of our 194 as shown earlier. So that's basically our CRC12 circuit. Now, what about this 4516 IC, or specifically we use the 4029 IC. Now this 4029 IC is basically an optional IC that basically serves as a counter. It basically counts if the user has already inputted 12 zeros. So after 12 zeros, the CRC clock will stop, which will automatically latch the CRC circuit. So instead of manually counting and manually latching the output, we have an automatic system to deal with that. And that is all for our conceptual schematic. Now let's move on to our proper and our actual schematic, which is in the ECEDA application. Now here we are on ECEDA, in which I'll be showing you our actual schematic for our PCB design. So we still have the same flow. We have the 164 IC for our serial input, parallel output, shift register. We also have this 74194, just like what I've shown earlier. We still have the 55 timer. Now, in our 5-volt regulator, we have some minor changes. Instead of using a battery directly, we'll be using these terminal blocks or connectors. Then we also added this diodes, two diodes that serve as a reverse polarity protection. So whenever we apply the wrong polarity in our circuit, they will protect basically the IC, every single IC, since they will immediately short the reverse polarity. And then we also have these decoupling capacitors, which will be placed near every IC. So that's a few changes for our 5 volts regulator. We still have the 12 zero counter, in which case we use the CD4029. And then we also have this 7486 IC, which are the XOR gates IC. We also have these LEDs from C12 to C1. C12 as the most significant bit, and C1 as the least significant bit. And we also have this green LED as shown earlier in the concept schematic. And then we added another LED for power. This will light up when power is supplied to the circuit. Another change is this one. We have these connectors. Instead of directly wiring the push buttons, which I will be discussing why later. So that's basically our schematic. Now let's move on to our PCB design. So here is our PCB design. So we have the ICs, the LEDs right on the top, the timer right over here, terminal blocks, and yeah, it's basically the design of our CRC-12 circuit. And we've used the ground plane methods to reduce the noise in the circuit basically. So this is our PCB design. As you can see, we have the LEDs on the top, their corresponding resistors. We have the shift register and XOR right in the middle. We have the decoupling capacitors near every single IC. So we have C6, C3 decoupling capacitors. Right over here is the CD4029, our 12 zero counter. And then we have our clock right over here. The terminal blocks on the bottom, which I'll be discussing later, why we have terminal blocks right over there. And this terminal block is for power. We have a power switch connected through these blocks here. And here is our design in a 3D render. So as you can see, we can see the traces at the bottom. And it looks nice actually. I love our CRC-12 design. Now, let me discuss what are these terminal blocks supposed to do? What are the purpose? So these terminal blocks will be connected external. They will provide external connection into a controller. And this controller will control the input and the reset of our CRC-12 circuit. So let's go and check out our CRC-12 PCB, actual PCB circuit. And let's have a little demo on how to use this CRC-12.
For our PWM circuit, we first have the two main components. First, the NE555 timer IC, which normally creates a square wave output. With the addition of a 1N4148 diode, we can create a sawtooth waveform. For the second component, we have a comparator in which we input the output of the 555 timer to the inverting port and the modulating signal to the non-inverting port. So as you can see, we first have the 300 ohm resistor and the 100 nanofarad capacitor. This serves as the frequency setter for our circuit. Next, you can see in the output of the 555 timer, we have the capacitor, the 1 microfarad and 1k ohm resistor, together with the potentiometer connected, which is set at 3.9 kilo ohm, which serves as an attenuator for the output of the 555 timer. Next, we have another 1 microcapacitor and an 8 kilo ohm resistor, which is also a potentiometer but is set at 8 kilo ohm, and a 20 kilo ohm resistor. These components serve as attenuators. No, these components serve as offset for the output of the 555 timer. Next, we have the 5.8 kilo ohm potentiometer and the 20 kilo ohm resistor for the input of the modulating signal. This also serves as offset for its output. Combining these outputs of the attenuated modulated signal and the attenuated sawtooth signal from the NE55 timer, we input these into the comparator. Now, we use another attenuating circuit with a 1 kilo ohm resistor, a 2 kilo ohm resistor to regulate the output. Overall, we have our desired output of the PWM or pulse width modulation circuit.
Hello. So here's our CRC-12 circuit. There we have it. And its top portion, we can open it. And then here is our controller. So it has a green LED, which will be in sync with the clock in the board. And we also have this red LED to indicate if it is connected or not. Then we have these two buttons, this button right over here to input a bit of 1, and this one for reset. So let's try it out. So let me power up the CRC-12 first. So as you can see, it's all powered up and the clock is already running. Now let me connect the controller. And its port is right here. So the controller is on, and if I input a 1, the blue LED is moving right over here, and the green LED between the controller and the board are in sync. So that's one of the features we have in our circuit. So let's actually try and demonstrate the CRC-12 process by using some input messages as examples. So here's our CRC-12 circuit in close-up view. So let me power it up first. There we have it, and then let me connect the controller right over here in its port. Look at the green LED, they are in sync. The red LED means it is connected. Now this button right over here is to enter a bit of 1, and then this one will enter a bit, or rather it will reset the whole CRC-12 circuit. So let's try our first example, which is the input message of polynomial 1. So let me press it once. And with this input, our expected output will be LED 12, LED 4, 3, 2, and 1 will lit up after 12 zeros. And there we have it, LED 1 right over here, LED 2, 3, 4, and the last LED lit up. Now let me append that remainder to our original message. So let's try it. So we have input 1, and then the remainder 1, and if I recall correctly, it has 7 zeros, so 4, 5, 6, 7. Then let me input 1, 2, 3. We have a 0 output. It means our CRC-12 remainder is correct. Let me reset. And let's try the next example, which is x squared plus 1 as the input. So this is x squared plus 1, x squared plus 1. And let's wait for 12 zeros. 5, 6, 7, 8, 9, 10, 11, 12. And it will automatically latch its remainder. LED2 and LED6, yes, it is correct. Let's actually append that remainder to our original message. So we have 6 zeros followed by a 1, 3 zeros, then followed by a 1. Let me append that. So we have x squared plus 1, and then we have 6 zeros. 4, 5, 6, followed by a 1, 1, 2, 3, and followed by another 1. As you can see, the output is all zeros, which means our CRC-12 remainder is correct. Now let's try another one, our last example, the most complex example, which is 1, 0, 1, 0, 1, 0, 0, 0, 1, 1, and 1. So that is our last example, which is the most complex one. And let's wait for the 12 zeros. And it will automatically latch its remainder. So we have 1 0 0 1 0 1 0 0 1 1. Let me memorize that. All right, let's try it. 1 0 0 1. So let's input the original message first, which is 1 0 1 0 1 0 0 0 1 1 1, and then the remainder, which is 1 0 0 0 1 0 1 0 0 1 1, and lastly 1. There we have it. We have all 0 as the output, which means our CRC-12 remainder and overall our CRC-12 circuit actually works with the addition of this controller.
For our PWM simulation results, as you can see, we have created a digital pulse train in which its pulse width varies in according to the amplitude of the analog signal or the modulating signal. For my learnings in this project in which we created a CRC-12 and PWM circuit, it helped me understand the fundamental theories behind the CRC-12 and the PWM circuits. And it also helped me bond with my partner and as well as further add to my foundation in PCB making and creating circuits.
Now let's discuss what I've learned during the process of building this project. So for PWM, I learned that there are two types of PWM, air quotes two types, depending on their use or functionality. So the first PWM is the one that is used to drive an LED or control the servo motor. And the PWM that we used is the analog modulation itself. the analog or the digital modulation. Now, the second thing I've learned is that I've learned how to create the circuit that will basically output a PWM signal, specifically PWM that has a analog signal as one of the inputs. Then lastly, I learned more about the functionality of the different ICs that we used in this project. So for example, the 555 timer, during the making of this project, I've learned that I can actually use it as a sawtooth generator and how to use the comparator IC. Now for CRC-12, I managed to learn how to handle digital circuitry because, first of all, this is my first time handling digital circuits. So I've learned various techniques such as using pull up and pull down resistors to decrease the sensitivity. And I've also learned about input bouncing, which is a common issue in digital circuits, and how to debounce the input. And basically the essence of applying decoupling capacitors in every IC, which factors in the reliability of the IC. The next thing I've learned is to implement the CRC-12 itself, the CRC-12 checking. And basically the whole circuit is the testimony of what I've learned regarding CRC. So the next thing I've learned is, I learned a lot about the different ICs. And for this project, for the CRC-12 project, I actually opened around 12 datasheets, more than 12 datasheets, just to check which among the various ICs there is that will fit with what we want for our project. And lastly, I've learned about optimizing and implementing additional unique features, creative features in our project. So first of all, the optimization aspect, which is we've managed to fit the whole CRC-12 with just 2 shift registers, which is quite difficult, and actually it is very efficient since all of the pins are used. And regarding the additional feature, which is the counter, the 12 zeros counter, so that's another one that I've learned. And the controller, the creative aspect, which is the controller, having an additional or external, something that will play around, that will increase the uniqueness of our project basically. And that is all for what I've learned with our projects.